we have three variables, there are a number of patterns of paths that we can have. This is the simplest one, the chain. We can also use the chain to represent a statistical model that is common in research, which is the mediation. So we say that the relationship between one variable and another one is mediated. So here we can represent that. So here we've got the variable x that causes v, and v causes y. Now, you can see that there is no arrow between x and y. That means that there is no direct causal link between x and y. What we can say in this case is that the effect of x and y is fully mediated by v. Okay, so there is if you study statistically, you will find a relationship between x and y. If you intervene in x, it will have an effect on y, but that effect will be because of what happens in v and nothing else. In that case, the effect of x and y is fully mediated by v. Let's see an example. We practice, that creates a change in the volume of muscles, and that is what causes a change in performance. So muscle volume fully mediates the effect of practice on performance. That means that there is nothing else that practice improves that will affect performance. Now, this is a different path. We have the chain and the mediation, but there is also a link between x and y. So x and y are connected by two paths. The direct path from x and y, and the indirect path that goes x to v, v to y. So in this case, that means that even though x produces a change in v and that change produces a change in y, also x produces a change in y directly. So in this case, the effect of x and y is mediated, but it's not fully mediated by v. Another pattern that we can find with three variables, which is called the common cause or the fork. So x and y are two variables that have a common cause. So there is a variable that, when we put u, is unknown, that is producing changes in x and y. Now, this is a problem when we try to find a causal link between x and y. Because if this is the case, we try to find a link between x and y, and the fact that u is causing changes in x and causing changes in y at the same time is what we call it confounding. Why confounding? Because let's say I study x, I observe changes in x and observe changes in y, and they seem to go together, so probably there is a causal link between x and y. But that's what we call correlation. But perhaps that relationship is because u affects x and u affects y, but there is no causal link between x and y. So because of this confounding that this graph allows us to visualize, we need to do something about it if we really want to understand the relationship between x and y. There are two things we can do to deal with this issue of confounding. We can make an intervention on X by randomly allocating participants to values of X, which means that we assign randomly participants to a group in which the value of X will be a specific value, and we assign other participants to a group in which the value of X will be different, and then we observe the effect on Y, and we do that allocation of participants in a randomly fashion. So that's one way we deal with confounding. And this way of dealing with this confounding works in this way, because the unknown variable may still have an effect on Y, but because I fix the values of X myself, then I disturb the connection between U and X, if that exists. So that connection disappears, and therefore now if I find a relationship between X and Y, it will be because X and Y are causally related, not because there is another confounding variable that affects both, because I blocked the effect of U on X. Another way of dealing with this is if you know the variable U, because sometimes you don't know it. So if you know the value U, the variable U and the values that participants obtain in that variable, then you can control U. And that's statistical tool, which basically what it does is to examine the relationship between X and Y at a fixed value of U. For example, in this case, we are trying to understand the relationship between X and Y, which is practice in a board game, X, to specific knowledge on that board game. So we want to know whether practicing a game increases your knowledge about that game. Now, there is a collider, Z, which is performance in that board game. So it's very intuitive to assume that X, practicing a board game, affects performance in that board game. So if you practice more, you get better at it. But also that the knowledge you acquire in that game makes you better at that game. Now, in order to analyze the relationship between X and Y, we need a range. So people who practice not too much, people who practice a little bit, people who practice a lot, and a range of people with knowledge in the game. So from knowing very little to knowing quite a lot, and a range in performance. So people who perform not so well and people who perform very well. But if we say, oh no, let's control for performance, well, what you are doing is the following. You take a group of participants with high performance, and in that group, you study the relationship between X and Y, between practice and specific knowledge. And you may have no relationship there because people who are at high performance levels, they tend to practice a lot and tend to know a lot about that game. You go to another group which has the same performance level, it's a bit lower. Well, they tend to have the same level of practice and same level of knowledge. So there is no relationship. So when you control for Z, you dilute the relationship between X and Y. If you have a wide range of values of Z, Y, and X, then you will find that people who practice more tend to have more knowledge in that game. There is another example which goes in the opposite way. So in this case, we change y. Instead of having knowledge on the board game, we've got working memory capacity. So in this model, because there is no arrow between x and y, we are saying that x and y are not related. So practice in a board game will not increase working memory capacity. But we are saying that practice in that board game increases performance in that game. And working memory capacity also has an influence on performance in that game. But x and y are not related. Now again, if we control for z, we are going to create a relationship between x and y that was not there before. Why? Well, let's say instead of measuring the relationship between y and z and x and z at all levels of z, we do this study at one level of z. Let's say people who have people who have a medium level of performance in z. But all the participants have the same level. Now, think about it. People who have practice a lot, then they should have lower working memory capacity at this if they achieve the same level. Because if they have a large working memory capacity, they should be performing at a higher level. But because they are performing at this level, at this medium level, if they practice a lot, that's because their memory capacity is not too good. On the other hand, if in this group of people who perform at medium level, we find someone who has very strong working memory capacity, well, it is likely that it's not practicing too much, because if it's practicing more, the level would be higher. So basically you introduce a negative correlation between x and y. So people who have at the same level of performance, people who have strong working memory capacity tends to have low practice board hours of practicing in the board game, and the other way around. So there is a negative relationship that is completely spurious, and we introduce it by doing this controlling for performance in a board game or variable z, the collider. So when there is a collider, do not control for it.